Hello and welcome back. In today's video, we're overclocking the AMD Ryzen 3 5300GE processor, that's a 35-watt APU, up to 4628 MHz, and the integrated graphics up to 2450 MHz. We do this using a GIGABYTE B550 Aorus motherboard and EK Quantum custom loop water cooling. This was a fun little system to play with in anticipation of the bigger launches this year, so I hope you enjoyed the video. The AMD Ryzen 3 5300GE is a 35-watt APU that is part of AMD's Zen 3-based Cezanne APU lineup. It sits alongside its 65-watt bigger brother, the 5300G. Launched back in April 2021, the AMD Ryzen 3 5300GE offers 4 cores and 8 threads with a listed base frequency of 3.6 GHz and a listed boost frequency up to 4.2 GHz. It also features an integrated Radeon Vega 8 GPU, which run at 1.7 GHz. The GIGABYTE B550 Aorus Master is a full-size ATX motherboard featuring the AMD B550 chipset. It offers a feature set usually found on the higher-end X570 lineup, such as a 16-phase VRM with 70 amps power stages, a thermal backplate, dual BIOS, and not one but 2 temperature sensors. In this video, we'll be covering 4 overclocking strategies. First, we enable Precision Boost Overdrive and enable XMP. Second, we tune the Precision Boost Overdrive parameters and use Curve Optimizer. Third, we go for a manual overclock on both the CPU cores and integrated graphics. Lastly, we try to supercharge Precision Boost Overdrive for maximum performance. However, before we jump into the overclocking, let's first have a look at the hardware and the benchmarks that we'll be using in this guide. Along with the AMD Ryzen 3 5300GE processor and GIGABYTE B550 Aorus Master motherboard, in this guide we will be using a pair of G.Skill Trident Z DDR4 4266 memory sticks, a 512GB Aorus RGB M.2 NVMe SSD, a 512GB Kingston HC400 SSD Now SSD, a Seasonic Prime 850W Platinum power supply, the Elmo Labs Easy Fan controller, the Elmo Labs power measurement device, the Elmo Labs EVC2, the EK Quantum magnitude water block, and EK Quantum water cooling. All this is mounted on top of our favorite Open Bench Table V2. The cost of the components should be around $2,292. I already explained how I use these different Elmo Labs products in SkatterBencher 34. By connecting the EFC and PMD to the EVC2 device, I monitor the ambient temperature, water temperature, fan duty cycle, and CPU input power. I include the measurements in my Prime 95 stability test results. I also use the Elmo Labs EFC to map the radiator fan curve to the water temperature. Without going into too many details, I've attached an external temperature sensor from the water in the loop to the EFC. Then I use the low-high setting to map the fan curve from 25 to 40 degrees water temperature. This is used for all overclocking strategies. We use Windows 11 and the following benchmark applications to measure performance and ensure system stability. Before we do any kind of overclocking, we must check the performance at default settings. But please note that the GIGABYTE B550 Aorus motherboard enables Precision Boost Overdrive by default. So if you want to check the performance at default settings, you first have to go into the BIOS and enter the advanced mode, go to the settings menu, enter the AMD overclocking submenu, set Precision Boost Overdrive to disable, then save and exit the BIOS. Here's the benchmark performance at stock. When running Prime 95 small FFTs with AVX disabled and FurMark concurrently, the average CPU cores run stably at 3621 MHz with 1.078 volts. The GPU operates at an average frequency of 1024 MHz with 0.767 volts. The average CPU temperature is 40.5 degrees Celsius. The water temperature is 27.6 degrees Celsius, and the average CPU package power is 35 watts. When running Prime 95 small FFTs with AVX enabled and FurMark concurrently, the average CPU cores run stably at 3392 MHz with 0.99 volts. The GPU operates at an average frequency of 752 MHz with 0.792 volts. The average CPU temperature is 39.9 degrees Celsius, the water temperature is 27 degrees Celsius, and the average CPU package power is 35 watts. For the different overclocking strategies, I will only report the non-AVX stability result because that kind of makes sense for this kind of a low-end system. All right, let's try our first overclock. But before that, make sure to locate the clear CMOS jumper. Shorting the clear CMOS jumper will reset all your BIOS settings to default. This is useful in case your system does not boot up after overclocking or if you want to start your BIOS configuration from scratch. In our first overclocking strategy, we simply take advantage of enabling Precision Boost Overdrive and enabling Intel Extreme Memory Profile. PBO stands for Precision Boost Overdrive and is an extension of the Precision Boost technology that is integrated into all AMD Ryzen CPUs. Precision Boost uses a proprietary algorithm with inputs from a plethora of sensors inside the CPU to determine the optimal frequency and voltage at any given time. Precision Boost allows the CPU to opportunistically increase its clock frequency over base frequency based on the available power and thermal headroom. Precision Boost Overdrive is the overclocker's extension of Precision Boost, as it provides us with tools to tweak the Precision Boost algorithm and achieve higher frequencies. It is important to mention that using Precision Boost Overdrive is a form of overclocking and is therefore not covered by warranty. When enabling Precision Boost Overdrive in the BIOS, the default power and current limits are unlocked and set the values that are pre-programmed by the motherboard BIOS. Note that while the power and current limits increase, the CPU operating frequency and voltage is still governed by AMD's Precision Boost algorithm. Extreme Memory Profile, or XMP, is actually an Intel technology that allows you to automatically overclock the system memory to get better performance. It's an extension of the JEDEC standard and allows memory vendors to program different settings onto the memory sticks. Those settings include the frequencies, the memory timings, as well as the memory voltage. There are two types of XMP certification. XMP Ready, where the module was programmed with an uncertain but stable profile, and XMP Certified, where the module was programmed with settings that have passed the supplier tests for the CPU and motherboard. I almost always run XMP on my systems because it's an incredibly easy way to get a little bit more performance. Do note that some motherboards might increase the CPU memory controller voltages to get really high frequencies stable. Upon entering the BIOS, in easy mode, set XMP disabled to XMP Profile 1. Then enter Advanced mode. Go to the Settings menu. Enter the AMD Overclocking submenu. Set Precision Boost Overdrive to Enabled. Then save and exit the BIOS. We rerun the benchmarks and check the performance increase compared to the default operation. We see performance improvements in all of our benchmarks, from single to multi-threaded CPU benchmarks to even GPU benchmarks. The GPU benchmarks have the biggest performance increase, as the integrated graphics benefits not only from the higher power limits, but also from the doubling of the memory frequency. We see the highest performance increase of plus 58% in FurMark 1080p. When running Prime 95 small FFTs with AVX disabled and FurMark concurrently, the average CPU cores run stably at 4193 MHz with 1.35 volt. The GPU operates at an average frequency of 2000 MHz with 1.408 volts. The average CPU temperature is 63.5 degrees Celsius, the water temperature is 29.1 degrees Celsius, and the average CPU package power is 109 watts. In our second overclocking strategy, we will make use of the overclocking tools provided by Precision Boost Overdrive 2. Together with the launch of the Ryzen 5000 desktop processors back in November 2020, AMD also launched Precision Boost Overdrive 2. When Precision Boost Overdrive 2 is enabled, the maximum operating frequency is governed by three major inputs: total socket power, the motherboard VRM current, and the CPU temperature. The System Management Unit, or SMU, on board the Ryzen CPU continuously monitors the system and decides to boost more or boost less. A key new feature of Precision Boost Overdrive 2 is called Curve Optimizer. Essentially, Curve Optimizer is a tool that provides users access to each of the CPU cores' voltage frequency curve and allows us to make adjustments to the voltage aspect of that voltage frequency curve. There are 6 key settings important when using Precision Boost Overdrive 2. I explored the ins and outs of each of the settings of Precision Boost Overdrive 2 in my Ryzen 7 5700G overclocking video, so I suggest that you check out that video if you want to learn more about the impact of each of these different settings. For PPT, EDC, and TDC, you can refer to the values shown in hardware info for reference. For example, in the Prime 95 non-AVX result from our previous strategy, we find that the maximum values for PPT, EDC, and TDC are 116 watt, 71.78 amps, and 43.7 amps. We can use values slightly higher than this to start the tuning process. For scalar, I usually set it to 10x as my cooling solution is not restrictive for the temperature increase associated with the increased voltage. The boost override I also immediately max out and set to 200 MHz. For Curve Optimizer, I configure a negative value for each core separately. Then I go into the operating system and check the initial core stability with a program called Core Cycler. When the core passes the quick stability test, I increase the negative offset. When the core doesn't pass, I reduce the negative offset. I also came across 2 unfamiliar settings called GFX Curve Optimizer and GPU Boost Clock Override. The latter I also came across when overclocking the Ryzen 7 5700G, but GFX Curve Optimizer was a new one. I did play around with both the Curve Optimizer and the Boost Override for the graphics portion, but the results weren't really that clear. In the end, I still got the same 2 GHz IGP frequency like I got when I was just enabling Precision Boost Overdrive, and the voltage wasn't really that different. At the end of the day, I settled for the following Precision Boost Overdrive values. Upon entering the BIOS, in Easy Mode, set XMP Disabled to XMP Profile 1. Enter Advanced Mode. Go to the Settings menu. Enter the AMD Overclocking submenu. Set Precision Boost Overdrive to Advanced. Set PBO limits to Manual. Set PPT limit to 135. Set TDC limit to 60. Set EDC limit to 80. Set SLC TDC limit to 60. Set SLC EDC limit to 80. Set Precision Boost Overdrive Scalar to Manual. Set Precision Boost Overdrive Scalar to 10x. Enter the Curve Optimizer submenu. Set Curve Optimizer to per core. Set Core 0, Core 1, Core 2, and Core 3 Curve Optimizer sign to negative. Set Core 0 Curve Optimizer magnitude to 25. Set Core 1 Curve Optimizer magnitude to 30. Set Core 2 Curve Optimizer magnitude to 20. Set Core 3 Curve Optimizer magnitude to 30. Leave the Curve Optimizer submenu. Enter the GFX Curve Optimizer submenu. Set GFX Curve Optimizer to GFX Curve Optimizer. Set GFX Curve Optimizer sign to negative. Set GFX Curve Optimizer magnitude to 30. Leave the GFX Curve Optimizer submenu. Set Max CPU Boost Clock Override to 200 MHz. Set Max GPU Boost Clock Override to 200 MHz. Then save and exit the BIOS. We reran the benchmarks and checked the performance increase compared to the default operation. After tuning Precision Boost Overdrive, we get a substantial performance uplift in the CPU benchmarks. That's mainly the effect of the Boost Clock Override providing an additional 200 MHz for the peak boost frequency as well as the Curve Optimizer. We get the highest performance increase of plus 58% in Firmark 1080p. When running Prime 95 small FFTs with AVX disabled and Firmark concurrently, the average CPU cores run stably at 4,397 MHz with 1.296 volts. The GPU operates at an average frequency of 2000 MHz with 1.379 volts. The average CPU temperature is 61.2 degrees Celsius, the water temperature is 28.9 degrees Celsius, and the average CPU package power is 104 watts. In our third overclocking strategy, we'll pursue a manual overclock. We'll focus on 4 different performance vectors: CPU core frequency, graphics frequency, memory frequency, and fabric frequency. Before we start though, it's important to know that AMD has 2 overclocking modes: Precision Boost Overdrive and OC mode. The first mode you already know, it's Precision Boost Overdrive. This mode allows the user to change a limited number of parameters that are included in the Precision Boost algorithm. However, it is still the AMD Precision Boost proprietary algorithm that will eventually determine the performance of the system. The second overclocking mode is called OC mode. OC mode disables all limits and most of the protections. A major downside of OC mode is that all the automatic overclocking features are disabled too. That means you lose the benefit of the high single-threaded frequencies that Precision Boost offers. As I mentioned earlier, the AMD Ryzen 3 5300GE is part of AMD's Cezanne APU lineup. Cezanne is a single CCD product that features Zen 3 cores. CCD stands for Core Chiplet Die and is just a die on the Ryzen CPU that has CPU cores and a shared L3 cache. The Zen 3 CPU cores are packed together in what's called a CCX or core complex. A Zen 3 CCX consists of up to 8 individual cores, each with its L1 and L2 cache and a shared 16 MB of L3 cache. The 5300GE only has 4 out of the 8 Zen 3 cores enabled, and also only has half of the L3 cache. The frequency of the CPU cores is driven by a 100 MHz reference clock input. Each CCX has its own PLL and thus can run an independent frequency. The cores within the CCX share the same PLL, so they'll run at the same frequency. The voltage of the CPU cores is provided by the VDD-CR CPU voltage rail. This voltage is shared across all the CCDs, so each CPU core will be provided with the same voltage. That said, AMD extensively uses integrated voltage regulators. The voltage regulators are ultra-high efficiency digital low dropout or DLDO. Most of the power domains, including the CPU cores, caches, fabric, and so on, have their own DLDOs, which can be controlled individually. However, on consumer parts, these DLDOs are permanently bypassed. That means the regulators are disabled and the voltage regulation takes place on the motherboard via the VRM. Choosing the right manual voltage is always going to be a trade-off between finding additional headroom for overclocking, fighting the thermal constraints or the thermal challenges that occur with increased voltage, and of course also taking into consideration the CPU lifespan. For this manual overclock, I used a voltage of 1.4 volt, which is about 100 millivolts higher than what the Precision Boost algorithm would boost to when we enable PBO. This allowed us to hit a CPU frequency of 4.5 GHz. Under a heavy load, the voltage drops to about 1.38 volt. AMD Cezanne APUs also come with Vega 8 based integrated graphics and normally have 8 compute units. However, our 5300GE is once again cut down as we only have 6 compute units. The frequency of the integrated graphics is driven by the same 100 MHz reference clock input as the CPU cores, though obviously it has a separate PLL. So the graphics frequency will not be the same as the CPU core frequency. The voltage of the GPU core is provided by the VDD-CR GFX voltage rail. However, this is not directly controlled by the motherboard voltage regulation. The Cezanne APU has 2 main power domains, one for the CPU and one for the SoC. We covered the CPU power domain in the previous segment and thus know the CPU cores are powered via the VDD-CR CPU voltage rail. The SoC is powered by the VDD-CR SoC voltage rail. The next part I wasn't able to fully confirm with technical specification or datasheets, but I think it's pretty accurate nonetheless. We know from the Ryzen Master reference guide that the graphics voltage is derived from the SoC voltage. So what's possibly happening is that the VDD-CR GFX voltage rail is either controlled via the DLDO integrated voltage regulation, or when DLDO is bypassed, directly derived from the VDD-CR SoC voltage rail. As I already mentioned, on consumer parts, the DLDOs are disabled by default. The bottom line is that when you want to overclock the integrated graphics and add some voltage, you will always also be adding voltage to the SoC. When we enable Precision Boost Overdrive, the voltage for the graphics as well as for the SoC goes up to 1.4 volt. That helps the GPU frequency go up from 1.7 GHz to 2 GHz. For our manual overclock, we increase the voltage by about 25 millivolts. That brings the voltage to 1.425 volt, but it helps us to further increase the graphics frequency to 2450 MHz. Cezanne supports up to 2 channels of DDR4 memory. Now, while the official specification is only guaranteed up to DDR4 3200, we know from all of the overclocking results out there that AMD Cezanne is pretty good at memory overclocking and goes even all the way up to DDR4 6000. Apart from the obvious side note that these overclocking records are performed using liquid nitrogen cooling, there's another important note on increasing performance through memory overclocking, the fabric clock. To make a long story short, there are 3 relevant frequencies when it comes to system memory performance. M clock or memory clock is the frequency of your DDR4 memory. U clock or memory controller clock is the frequency of the integrated memory controllers. F clock or fabric clock is the frequency of the Infinity Fabric. When the CPU cores want to store data to or retrieve data from the system memory, it does this via the Infinity Fabric and the memory controllers. By default, these 3 parts are running in sync, meaning they all operate at the same frequency. When overclocking the system memory, you can choose to either operate in synchronous mode or asynchronous mode, but more on that in the next segment. The memory frequency is driven by the same 100 MHz reference clock also used for the CPU cores and integrated graphics. For our manual overclock, we will still rely primarily on the XMP profile, so we load in all of the timings, the voltage and the frequency, but we change the frequency and the voltage. So we change the frequency from DDR4 4266 to DDR4 4533, and we increase the voltage from 1.4 volt to 1.45 volt. The additional memory performance is not only going to help us in the CPU benchmarks, but it's also going to help us in the GPU benchmarks, as the integrated graphics relies on the system memory. As I mentioned in the previous segment, the Infinity Fabric also provides the CPU cores and dies with access to the other SoC components like PCIe, USB, SATA, and so on. It also provides access to the memory controller via which the CPU can communicate with the system memory. By default, the Fabric, memory controller, and memory frequency operate in synchronous mode. That means the CPU will run all frequencies in a 1-to-1 ratio. Synchronous mode is relatively taxing for the CPU, so on most Ryzen CPUs, the system will automatically enable asynchronous mode beyond a certain memory frequency. In asynchronous mode, the memory controller will operate at half the frequency of the system memory, and the fabric clock will also run below the system memory frequency. This will result in a performance penalty. The size of the performance penalty is application specific and also depends on the final memory frequency. A sufficiently high memory frequency can overcome the performance penalty from running in asynchronous mode. In the case of the Cezanne APU, we definitely want to try to run in synchronous mode because, well, not only the CPU cores want fast access to the system memory, but also the integrated graphics heavily relies on the performance of the system memory. Fortunately, the Cezanne APU has a couple of aspects to it that make it a really good prospect for high fabric frequency. First, as AMD pointed out when launching the Ryzen 5000 series, the Zen 3 architecture should have a slightly improved range for fabric overclocking. They suggested that DDR4 4000 memory with a 2 GHz fabric clock is the new standard with the 5000 series. Second, APUs in particular have a design advantage as well. The CPU cores and cache, the integrated graphics, and the I/O are all integrated into a single die. That's different from a single CCD Ryzen 5000 CPU, for example the Ryzen 5 5600X, which still has a separate I/O die on package. This effectively means the Infinity Fabric is entirely integrated inside the single die and thus allows for a much higher overclocking range. Whereas we sometimes struggle to run in synchronous mode at DDR4 4000 on regular Ryzen 5000 desktop CPUs, on this APU we were able to quite easily run at DDR4 4533 with a synchronous fabric clock of 2267 MHz. Upon entering the BIOS, in easy mode set XMP disable to XMP profile 1, then enter advanced mode. Set CPU clock ratio to 45. Set GFX clock frequency to 2450. Set GFX core voltage to 1.425. Set system memory multiplier to 45.33. Set F clock frequency to 2267. Set CPU vCore to 1.4. Set DRAM voltage to 1.45. Enter the CPU VRM settings submenu. Set CPU vCore load line calibration to high. Set vCore SoC load line calibration to high. Then save and exit the BIOS. We reran the benchmarks and checked the performance increase compared to the default operation. Our manual overclock of 4500 MHz is higher than the maximum precision boost overdrive frequency of 4450 MHz. Hence, we see a performance uplift in all CPU benchmarks. Furthermore, the integrated graphics frequency increase from 2000 MHz to 2450 MHz provides a lot more performance in 3D benchmarks as well. We get the highest performance increase of plus 69% in Furmark 1080p. When running Prime 95 small FFTs with AVX disabled and Furmark concurrently, the average CPU cores run stably at 4460 MHz with 1.38 volt. The GPU operates at an average frequency of 2450 MHz with 1.416 volts. The average CPU temperature is 68.3 degrees Celsius, the water temperature is 29.1 degrees Celsius, and the average CPU package power is 123 watts. In our fourth and final overclocking strategy, we will try to supercharge Precision Boost Overdrive and try to get even more performance. I explained what I mean by supercharging Precision Boost Overdrive in 3 previous SkatterBencher videos. Episode 26 with the 5900X, episode 27 with the 5950X, and episode 29 with the 5900 B2 stepping. It's quite a lengthy explanation that I did in those videos, so if you want to have really a detailed look at what I mean by supercharging, I would suggest you to go and check out those videos. The long story short is that we use reference clock overclocking and voltage offsets to manually change the voltage frequency curve. The voltage frequency curve, or VF curve, is a line that describes the relationship between the operating frequency and the voltage required to run stably at that frequency. Every core in your AMD Ryzen CPU has a VF curve. Better cores, which require less voltage for a given frequency, will be able to boost to higher frequencies given a certain voltage. Precision Boost technology uses this VF curve information to dynamically increase the CPU operating frequency. The boost algorithm determines the maximum allowed voltage for a given set of input parameters. The inputs include not just power, current, and temperature, but also the number of active cores, the core quality, and so on. Once the algorithm has determined the maximum allowed voltage, it applies the corresponding frequency based on the VF curve. The Precision Boost algorithm assumes the reference clock is 100 MHz and is unaware of any user changes. We can exploit this and use the reference clock to push the core frequency higher than what the algorithm wants to set it at. For example, if the algorithm pushes the frequency to 4500 MHz and we use a base clock frequency of 101 MHz instead of the default 100 MHz, then the actual frequency will be 4500 times 1.01 equaling 4545 MHz. While this may sound simple and straightforward, there are a couple of caveats. First, the reference clock frequency drives many parts in your system. including the CPU cores, but also the system memory, PCIe, and SATA. When increasing the reference clock, you change all associated frequencies as well. While this can result in additional performance, it can also cause instability. Fortunately, for most parts affected by the reference clock, we can adjust the final frequency using multiplier ratios. Unfortunately, not for all. The main challenge with using reference clock adjustments on Ryzen is bus interfaces like PCIe, SATA, and NVMe drives. On this particular board, when the reference clock frequency exceeds 104 MHz, the NVMe drives are no longer detected. So we have to use a SATA drive connected to the S-Media B550 chipset. Second, as the algorithm is unaware of the increased frequency, it will also not adjust the voltage accordingly. By adding a voltage offset, we can look for stability at the highest frequency range. But keep in mind that adding an offset to the entire VF curve means that you'll also get higher voltage at lower frequencies. In heavy multi-threaded workloads, that means you'll run out of thermal headroom faster than without the voltage offset. Third, just like any motherboard, the B550 Aorus Master has a lot of BIOS auto rules to help with easy overclocking. However, the same auto rules that help make manual overclocking amazingly easy can sometimes make overclocking with Precision Boost Overdrive trickier. When increasing the reference clock to over 104 MHz, the auto rules of the BIOS force the CPU into OC mode and thus has all Precision Boost functionality disabled. So you'll end up with a fixed ratio in the operating system. There are no options in the BIOS to work around this issue, so unfortunately 104 MHz is the maximum base clock frequency for our supercharged Precision Boost Overdrive strategy. GIGABYTE did provide me with a test BIOS that addressed this specific auto rule. So I was able to try higher than 104 MHz BCLK with Precision Boost Overdrive enabled. However, it did result in some other instabilities, so I wasn't quite able to improve my overclock. Anyway, now that we know how to supercharge Precision Boost Overdrive, let's go into the BIOS and configure our overclock. Upon entering the BIOS, in easy mode, set XMP disabled to XMP profile 1. Enter advanced mode. Set CPU clock control to 104. Set GFX clock frequency to 2350. Set GFX core voltage to 1.425. Set system memory multiplier to 42.66. Set F clock frequency to 2133. Set CPU vCore to normal. Set dynamic vCore DVID to plus 0.03125. Set DRAM voltage to 1.5. Go to the Settings menu. Enter the AMD Overclocking submenu. Set Precision Boost Overdrive to Advanced. Set PBO limits to Manual. Set PPT limit to 150. Set TDC limit to 60. Set EDC limit to 85. Set SoC TDC limit to 60. Set SoC EDC limit to 85. Set Precision Boost Overdrive Scaler to Manual. Set Precision Boost Overdrive Scaler to 10x. Enter the Curve Optimizer submenu. Set Curve Optimizer to per core. Set Core 0, Core 1, Core 2 and Core 3 Curve Optimizer sign to negative. Set Core 0 and Core 2 Curve Optimizer magnitude to 5. Set Core 1 and Core 3 Curve Optimizer magnitude to 10. Leave the Curve Optimizer submenu. Set Max CPU Boost Clock Override to 200 MHz. Then save and exit the BIOS. We reran the benchmarks and checked the performance increase compared to the default operation. In most benchmarks, we achieved the best performance thanks to a supercharged Precision Boost algorithm boosting the CPU to higher frequencies. In some benchmarks, the performance is matched by our manual overclocking result. Overall, we see the highest performance improvement of plus 67.35% in Furmark 1080p. When running Prime 95 small FFTs with AVX disabled and Furmark concurrently, the average CPU cores run stably at 4432 MHz with 1.409 volts. The GPU operates at an average frequency of 2444 MHz with 1.38 volt. The average CPU temperature is 68.7 degrees Celsius. the water temperature is 28.5 degrees Celsius, and the average CPU package power is 125 watts. When running Prime 95 small FFTs with AVX enabled and firmware concurrently, the average CPU cores run stably at 4424 MHz with 1.399 volts. The GPU operates at an average frequency of 2444 MHz with 1.38 volts. The average CPU temperature is 75.1 degrees Celsius, the water temperature is 29.3 degrees Celsius, and the average CPU package power is 139 watts. Alright, let's wrap this up. I put together this system because I figured it would be interesting to see what the most entry-level Ryzen 5000 processor would be capable of. And boy, is this entry-level. This is a 35-watt APU with only 4 Zen 3 cores available. But to give us the highest chance at a big overclock, I did pair it with a relatively high-end B550 motherboards from Aorus, as well as EK custom loop water cooling. In the end, we managed to push the CPU from being limited to only 35 watt to almost reaching 140 watt. That's a quadrupling of the power consumption. In terms of CPU overclocking, we managed to increase the single-threaded boost frequency from 4,250 MHz to 4,628 MHz, so almost 400 MHz. And we also managed to increase the AVX multi-threaded frequency from about 3.4 GHz when it's limited to 35 watt to 4,400 MHz when we essentially let it boost to however high it wants to go. And that's almost a 1 GHz overclock. The integrated graphics also overclock quite nicely, going from 1.7 GHz to 2.45 GHz. The Infinity Fabric was able to run in synchronous mode with the memory at 2267 MHz, so the memory was running at DDR4 4533, and I think we were limited here by our memory. So I think maybe there's even more stretch in the fabric frequency on this particular chip. It's always fun to overclock Ryzen APUs, not only because the single CCD design allows for easier memory and fabric overclocking, but also because there's an opportunity to try and tweak the integrated graphics as well. That said, this Ryzen 3 5300GE definitely felt as if it was the bottom of the barrel when it comes to Ryzen 5000 processors. So I wouldn't quite recommend you to go out, buy one, and play around with it yourself. Also, because it would be quite difficult to get your hands on it, it's an OEM exclusive, so they're not readily available in retail. Anyway, that's all for today. As you may have seen on my Twitter and my community posts, I am kind of trying to get my head around how to overclock a 64-core Threadripper 3990X processor. So I'm hoping to get that video out as soon as possible as well, so I can share my experience with you as well. As per usual, if you have any questions or comments, feel free to drop them in the comment section below. And till the next time.